19 brake systems, certified, approved, and installed on commercial aircraft. Every single one of them had the same failure mode already documented in testing. Engineers knew. Regulators saw the data. The planes flew anyway. This is not a conspiracy theory. This is what happens when you dig into the Federal Aviation Administration archives from the 1960s and 70s and find out exactly how many corners got cut in the name of keeping production schedules moving. Some of these decisions make perfect sense when you understand the context. Some of them should never have happened. And if you have ever wondered why modern aviation certification takes so long and costs so much, the answer is written in the wreckage of every shortcut that came before. Hit subscribe right now, because what I am about to walk you through is the kind of specific regulatory failure that most people have no idea even exists. Number 1. The Lockheed Electra's Power Brake Booster System. This was the brake system that defined early turboprop airliners in the late 1950s. Hydraulic power boost, short stopping distances, responsive pedal feel. Pilots loved it. The failure mode was simple and brutal. If you lost hydraulic pressure during landing, the brakes did not just get harder to press. They failed completely. No backup, no mechanical linkage, just a pedal connected to nothing. The regulation that followed required dual independent hydraulic systems with automatic crossover valves and a mechanical backup that could stop the aircraft even with total hydraulic failure. That is why modern airliner brake pedals feel different depending on which system is active. You can actually feel the switch happen if you know what to pay attention to. The Electra had none of that. Just one system, one failure point, and a documented history of runway overruns when that system failed. Beautiful engineering for its time, certified anyway, and completely illegal on anything built after 1965. Number 2. The Boeing 707's original anti-skid system. Anti-skid brakes were cutting-edge technology when the 707 entered service. Wheel speed sensors detected lockup and modulated brake pressure automatically. On dry runways, it worked brilliantly. On wet or icy surfaces, the system would occasionally interpret normal wheel slip as a skid and release all brake pressure at exactly the moment you needed it most. The failure mode was not a malfunction. It was the system working exactly as designed, just with sensor logic that could not tell the difference between a skid and a slippery runway. The FAA mandated revised sensor algorithms and fail-safe logic that defaulted to manual braking if the system detected conflicting data. Modern anti-skid systems use multiple redundant sensors and cross-check against ground speed radar. The original 707 system had one sensor per wheel and no cross-check. Pilots learned to disable it in bad weather. The system was certified with that limitation documented. It stayed in service for years. Number 3. The Douglas DC-6 Carbon Brake Disc Assembly. Carbon brakes were lighter than steel. They handled heat better. They were the future of aviation braking when Douglas introduced them as an option on late-model DC-6 aircraft. The problem was thermal shock. If you landed in heavy rain after a long descent, those carbon discs would go from several hundred degrees to near freezing in seconds. The disc would fracture, not wear down, fracture. Pieces of carbon brake disc would separate and jam the wheel assembly. The regulation that ended this specific design required carbon brake discs to pass thermal shock testing that cycled them through extreme temperature changes hundreds of times without structural failure. Modern carbon brakes use composite layering and controlled porosity to handle thermal expansion. The DC-6 discs were solid carbon. Lighter, yes, also brittle in exactly the conditions where you needed brakes most. The failure mode was documented in the certification testing. The system was approved with a restriction against operation in freezing precipitation. That restriction was unenforceable and everybody knew it. Number 4. The Convair 880's Brake Temperature Monitoring System. This was the first airliner to include cockpit brake temperature gauges. Pilots could see exactly how hot their brakes were getting during taxi and landing. The system used thermocouples embedded in the brake housing. Here is the problem. By the time the thermocouple registered dangerous temperatures, the brake was already past the point of safe operation. The lag time was sometimes over a minute. Pilots would see normal temperatures, continue taxiing, and then watch the gauge spike into the red after the damage was already done. The regulation that came after required real-time brake temperature monitoring with alerts based on rate of change, not absolute temperature. If your brakes are heating faster than normal, you know immediately. The Convair system told you after the fact. The failure mode was timing. The certification documents noted the lag. The system was approved because it was better than no monitoring at all, which was the standard at the time. Better than nothing became the baseline. That baseline killed people. Number 5. The Vickers Viscount's Hydraulic Accumulator Design. The Viscount used a single hydraulic accumulator to maintain brake pressure during engine shutdown and ground operations. Elegant, simple, effective, until the accumulator diaphragm failed. When that diaphragm ruptured, hydraulic fluid would mix with the nitrogen charge and you would lose all stored brake pressure in seconds. No warning, no gradual decline, just full brakes one moment and nothing the next. The failure happened most often during cold weather operations when the diaphragm material became brittle. Modern systems use multiple accumulators with pressure sensors and automatic isolation valves. If one fails, the others take over and the cockpit gets an immediate alert. The Viscount had one accumulator and no monitoring. The failure mode was documented in testing. The certification included a maintenance interval for diaphragm replacement. That interval was based on calendar time, not cycles or inspections. Diaphragms failed early. The interval did not change for years. 6. The Fokker F-27's brake master cylinder seal. This was a straightforward hydraulic brake system. Master cylinder in the cockpit, slave cylinders at each wheel. The seals in the master cylinder were made from a synthetic rubber compound that degraded when exposed to certain hydraulic fluids. Not all fluids, certain ones. If you serviced the system with the wrong fluid, the seals would swell, stick, and eventually fail to return to neutral. Your brakes would drag constantly. Taxi would overheat them. Landing would finish the job. The regulatory fix was simple: mandatory hydraulic fluid specifications and placarding requirements. You could only use fluids that were chemically compatible with every seal in the system. The F-27 certification documents listed compatible fluids. They also listed incompatible fluids. And then the aircraft was certified with a maintenance note that said use only approved fluids. The approved fluid was more expensive. The incompatible fluid was standard stock at half the airports the F-27 served. Mechanics used what they had. Seals failed. Everyone knew why. Number 7. The Hawker Siddeley Trident's brake cooling duct design. The Trident had ventilated brake discs with cooling ducts that channeled airflow during taxi and rollout. Smart design. Kept the brakes cooler, extended service life, reduced the risk of fire. The ducts were mounted low on the landing gear strut. During operations on wet runways, water and slush would spray directly into those ducts, hit the hot brake disc, flash to steam, and create pressure spikes that could blow seals and crack housings. The failure mode was not the cooling system. It was where the cooling system was positioned. Modern designs use check valves and drain systems that allow air in but keep water out. The Trident ducts were open. The certification testing was done on dry runways. The failure mode appeared in service, got documented in maintenance logs, and eventually made it into an airworthiness directive that required inspection after every wet runway operation. The system was not redesigned. The inspection interval just increased. Number 8. The Sud Aviation Caravels brake pressure regulator valve. This was a mechanical valve that limited maximum brake pressure to prevent wheel lockup and tire damage. It worked perfectly at sea level. At high-altitude airports where air pressure was lower and tire pressures were adjusted accordingly, the regulator would still limit brake pressure to the sea level maximum. Your tires had less grip because they were inflated to a lower pressure. Your brakes delivered less force because the regulator was calibrated for sea level. Stopping distances increased dramatically. The fix was an adjustable regulator with altitude compensation. The Caravelle had a fixed regulator. The certification documents included performance charts that showed increased stopping distances at altitude. Airlines were expected to account for this in their landing distance calculations. Some did, some did not. The failure was not mechanical. It was informational. Pilots did not always know their brakes were limited. The system worked exactly as designed. The design was just incomplete. Number 9. The Antonov An-24's pneumatic brake actuation system. Soviet design philosophy in the 1960s favored pneumatic systems over hydraulic where possible. Simpler, fewer seals, less fluid to leak. The An-24 used engine bleed air to actuate the brakes. High-pressure air pushed pistons that clamped the brake pads. Brilliantly simple, also temperature sensitive. Cold air is denser, hot air is less dense. Your brake pressure varied with outside air temperature. On a cold day at a Russian airfield, you had strong, responsive brakes. On a hot day in Africa or the Middle East, your brake pressure could drop by 30%. The system included a pressure compensator, but it was manually adjusted and most crews did not know it needed adjustment for temperature. Modern pneumatic brake systems use electronic pressure regulation with automatic temperature compensation. The An-24 had a manual valve and a placard. The failure mode was operator error caused by a design that required knowledge most operators did not have. It was certified. It flew for decades. Number 10. The BAC-111's brake wear indicator system. This aircraft used a simple mechanical pin that protruded through the brake housing. When the pads wore down, the pin would sit flush with the housing. Visual inspection. No gauges, no sensors. The problem was accessibility. You could only see the pin if you were on the ground, close to the wheel, with the gear fully extended and no covers in place. During pre-flight walkarounds, the pin was often obscured by the gear door, shadows, or dirt. Brakes would wear past minimums and nobody would notice until a mechanic did a detailed inspection. The regulatory change required wear indicators that were visible during normal walkaround inspections or had cockpit monitoring. Modern systems use electronic sensors that display brake wear percentage on a flight deck screen. The 111 had a pin you might see if the light was good. The failure mode was not the indicator, it was the location. Certification allowed it because it met the requirement for a wear indicator. Nobody said the indicator had to be easy to see. If you are the kind of person who wants to understand how aviation regulation actually works, how these systems were approved, and what changed after each failure, I have put together a detailed timeline of every major brake system certification failure from 1955 to 1985, including the specific regulatory changes that followed each incident. It includes the FAA documents, the accident reports, and the engineering analyses that were buried in archives for decades. Grab it at the link in the description. Number 11. The tuple of Tu-134's brake disc retention design. The Tu-134 used a keyed shaft system to hold the brake disc in place. The disc slid onto a spline shaft and was retained by a snap ring. Simple, lightweight, easy to service. If the snap ring failed or was installed incorrectly, the brake disc could walk off the shaft during braking. Not immediately. Gradually, a few millimeters per landing cycle. Eventually the disc would separate enough that brake pressure would drop to nothing. The failure mode was not the snap ring breaking. It was the snap ring being installed with the gap positioned incorrectly, allowing it to spread under load. The certification included installation instructions. The instructions were in the maintenance manual. The mechanics in the field were not always working from the current manual. Discs separated, planes overran runways. The design was not changed. The inspection interval was shortened. That was the fix. Number 12. The Ilyushin Il-18's dual brake pedal linkage. The Il-18 had two sets of brake pedals, one for the captain and one for the first officer. Both pedals controlled the same master cylinder through a mechanical linkage with a crossover bar. If one pilot pushed the pedals and the other rested their feet on their pedals without realizing, the forces would conflict and the master cylinder would receive inconsistent input. Your brakes would pulse, on and off, not a failure. Just two inputs fighting each other. The failure mode was human interaction with a mechanical system that had no priority logic. Modern fly-by-wire brakes have electronic arbitration. If both pilots press the brakes, the system takes the higher input. The Il-18 linkage added the forces together in a way that caused oscillation. It was certified because both pilots having brake authority was considered a safety feature. Nobody thought about what happened when both pilots used that authority simultaneously without coordinating. Number 13. The Canadair CL-44's brake hydraulic filter location. Hydraulic systems need filters. The CL-44 had a filter in the brake hydraulic line positioned downstream of the pump and upstream of the master cylinder. Standard design. The filter housing was mounted on the aft pressure bulkhead in the wheel well. During flight, that area would cool significantly. During descent and landing, the hydraulic system would heat up. The filter housing would contract and expand with temperature changes. Over time, the housing would develop microcracks. Hydraulic fluid would weep through the cracks, not a dramatic leak, a slow seep, but it would coat the brake assembly and the inside of the wheel well with flammable hydraulic fluid. Then you would land, your brakes would heat up, and you would have a fire. The failure mode was not the filter, it was where the filter was mounted. The regulatory fix required hydraulic components in wheel wells to be tested for thermal cycling, and any component that could leak had to be positioned where leaking fluid could not contact hot brakes. The CL-44 filter was repositioned in later production models. Early models kept the original location. Inspection intervals were added. Fires continued. Number 14. The Hanley Page Herald's brake pedal force feedback system. This aircraft had a mechanical linkage that gave the pilot direct force feedback from the brakes. You could feel exactly how much clamping force the pads were applying. Pilots loved it, great for smooth landings and taxi operations. The feedback mechanism used a spring cartridge in the pedal assembly. If that spring failed, the pedal would go to the floor with almost no resistance. You would have brakes. You just would not feel them. Pilots would instinctively push harder, thinking the brakes were not working, and lock the wheels. The failure mode was sensory, not mechanical. Your brakes worked fine, your feedback system lied to you. Modern brake systems separate the feedback mechanism from the actuation system. If feedback fails, you get a cockpit alert and the brakes still operate normally. The Herald had integrated feedback. When it failed, pilots got no warning, just a pedal that felt wrong. The certification documents noted that spring failure would result in altered pedal feel. That was considered acceptable because the brakes would still function. Nobody tested what pilots would do when the pedal feel changed suddenly during landing. Number 15. The Aero Commander's brake fluid reservoir vent design. Small thing, huge consequences. The brake fluid reservoir had a vent cap that allowed air pressure equalization during flight. The vent had a small filter to keep contaminants out. That filter would clog. Dust, dirt, insects, anything small enough would block the vent. Once the vent was blocked, the reservoir could not equalize pressure. As the aircraft climbed, the air pressure inside the reservoir would drop relative to outside pressure. The the fluid level would appear normal on the ground. In flight, the pressure differential would cause the fluid to foam and aerate. When you landed and applied the brakes, you were trying to compress aerated fluid. Your pedal would feel spongy. Your stopping distance would increase. The fix was a larger vent with a self-cleaning filter design. The original Aero Commander vent was tiny. It clogged constantly. The failure mode was documented in service bulletins. The design was not changed until the FAA mandated vent performance standards that required flow rates the original design could not meet. For years, the approved solution was to clean the vent filter at every inspection. Most mechanics did, some did not. Number 16. The Beechcraft King Air's parking brake ratchet mechanism. The parking brake used a ratchet and pawl system. You pulled the brake handle, a ratchet locked it in place, and your brakes stayed applied. The pawl was spring-loaded. If the spring weakened or broke, the pawl would not engage fully. The brake would hold for a few minutes, then slowly release. Your aircraft would start rolling. On a flat ramp, not a problem. On a slope, disaster. The failure mode was gradual spring fatigue. The spring was not considered a life-limited part. It was inspected visually. A weakened spring looked identical to a new spring unless you tested it under load. Modern parking brake systems use hydraulic or pneumatic locks with pressure monitoring. If pressure drops, you get a warning. The King Air had a mechanical ratchet and no monitoring. The certification included a maintenance inspection. The inspection checked if the brake held, not if the spring was weakening. Aircraft rolled away from chocks. Some hit other aircraft, some rolled into ditches. The spring was eventually added to the life-limited parts list. That took years. Number 17. The NAMC YS11's brake hydraulic line routing. The hydraulic lines that fed the brakes were routed along the landing gear strut. Normal design. The lines were secured with cushion clamps to prevent vibration damage. On the YS11, the clamps were positioned in a way that allowed the hydraulic line to contact the gear strut during certain loading conditions, not during normal operations, during hard landings or rough taxiing on uneven surfaces. The strut would flex, the line would rub, and over time the vibration and contact would wear through the hydraulic line sheathing. You would get a slow leak, then a fast leak, then no brakes. The failure mode was not the line, it was the routing and clamping design that allowed contact. Modern certification requires hydraulic lines to have clearance from all moving parts under all load conditions, including maximum deflection. The YS11 lines had clearance under normal loads. Maximum deflection was not tested. The wear pattern was discovered in service. An airworthiness directive required rerouting the lines. Early aircraft had the original routing for years before the directive was issued. Number 18. The Embraer Bandeirantes brake master cylinder check valve. Here is the one you have been waiting for. This killed more pilots than almost any other brake failure mode on this list. The master cylinder had a check valve that prevented brake fluid from flowing backward. When you released the brake pedal, the check valve closed and maintained residual pressure in the line. This gave you faster brake response on the next application. Brilliant idea. The check valve was a ball bearing and a spring inside a brass housing. If any contamination got into the system, a tiny particle of metal or rubber, it could lodge between the ball and the seat. The valve would not close completely. Brake fluid would flow backward. You would lose all brake pressure, not slowly, immediately. The failure mode was contamination in a system that had no filtration between the reservoir and the check valve. Modern systems have inline filters upstream of every critical valve. The Bandeirante had a filter at the reservoir. Anything that got past that filter could kill the check valve. The certification documents included a requirement for clean fluid during servicing. That was the contamination control. Fluid was not always clean. Valves failed. Aircraft crashed on landing. The fix was a filter addition and a check valve redesign that was more tolerant of contamination. That fix came after years of service and multiple fatal accidents. Number 19. The short Skyven's brake pressure accumulator precharge specification. Last one. The Skyven used a hydraulic accumulator to store brake pressure. The accumulator was precharged with nitrogen gas to a specific pressure. If the precharge pressure was too low, the accumulator could not store enough hydraulic pressure and your brakes would feel soft. If the precharge pressure was too high, the accumulator diaphragm could rupture and you would lose the accumulator entirely. The specification was narrow. The precharge equipment available in the field was not always accurate. Mechanics would charge the accumulator by feel or with gauges that were not calibrated. Accumulators would be overcharged. Diaphragms would fail. The failure mode was not the accumulator design. It was the lack of field equipment capable of reliably achieving the required precharge pressure. The regulatory fix required all life support and critical hydraulic systems to have precharge specifications that could be met with standard calibrated equipment. If your specification required precision that field equipment could not deliver, you had to redesign the system to be more tolerant. The Skyven accumulator specification was eventually widened. Early models had the tight specification. Diaphragm failures were common. The system was certified with the assumption that mechanics would have the right tools and training. That assumption was wrong. Every one of these brake systems was certified by a regulatory body that had the data. The failure modes were documented. The testing showed the problems, and the systems were approved anyway because the standard at the time was not zero failures. It was acceptable failures, acceptable losses. People who did not make it home because a check valve could not handle a particle of rubber or a spring was not on the life-limited parts list or a vent filter was too small. These were not dramatic, catastrophic failures. These were quiet, predictable, preventable deaths that happened because certification meant good enough, not safe. Next time you are on a modern airliner and you hear the hum of the hydraulic pumps or feel the brakes engage smoothly on landing, remember what it replaced. Every system on that aircraft exists because an earlier system failed and someone wrote it down. That is the cost of progress. That is why certification takes years now. That is why we do not cut corners anymore. Drop a comment and tell me which of these 19 failure modes shocked you the most. Next time I am taking you through cockpit instruments that were removed in the last 20 years that pilots never noticed were gone until someone pointed it out. Some of them you assumed were required by law. They are not. And the reasons they disappeared will change how you think about what belongs in a cockpit.